All right, picture this. You're stepping into a grand Victorian library. You know, the kind with dark wood, leather-bound books. A place where craftsmanship is everything. That's the world we're diving into today, the world of code craftsmanship. And we're about to uncover a silent, program-killing villain that lurks in the shadows of concurrent programming. So let's meet a developer who's about to face this villain head-on.
So, this is Timothy. He's our junior developer, and right now he's feeling pretty good about himself. He's just gotten the hang of using locks in Python to stop race conditions. You know the feeling. His code is finally working, his counters are spot on, and he's feeling confident. He thinks he's basically conquered concurrency.
But of course, a new challenge lands on his desk. He needs to build a system to move money between two digital vaults. We've got the entry fee vault and the prize pool vault. And here's the catch. The whole thing has to be thread safe. That's the key requirement. It needs to be an ironclad guarantee that no data gets messed up, even if a bunch of transfers try to happen at the exact same time.
Now, Timothy's logic, well, it seems perfectly sound, right? To stop any mix-ups, he decides that anytime a transfer is happening, he'll just lock both vaults, the one the money is coming from and the one it's going to. Simple. No other thread can touch them until he's done. So he designs two functions, one to go from vault 1 to 2 and another to go from 2 to 1. On paper, it seems simple, safe, totally foolproof. What could possibly go wrong? He runs the code. The program prints out a couple of lines and then nothing. It just stops. It hasn't crashed. There's no error message. It's just frozen. What's happening here is this perfect silent trap. See, thread A has successfully locked vault 1, and now it's just sitting there waiting for vault 2. But at the exact same instant, thread B has locked vault 2, and it's waiting for vault 1. They're at a total standstill.
So in a moment that I think every developer can relate to, Timothy is completely confused. He turns to his senior colleague, Margaret, and his description of the problem, it's just perfect. It's not a crash, it's a standoff. He says they're just staring at each other. Two parts of his program are locked in a digital staring contest, and neither one is going to blink.
And this is where Margaret, the senior engineer, comes in. She takes one look at the screen and, she immediately gets it. She knows exactly what's going on, and she gives this mysterious problem a name.
Now, the technical term for what Timothy's run into is a deadlock. This is a classic textbook problem in concurrency. It's what happens when two or more threads get stuck in this circular holding pattern. Each one is holding a resource that the other one needs to move forward, and since neither can proceed, they get locked in that state, forever. But Margaret gives it a much better, much more memorable name. She calls it the ultimate Mexican standoff. And that analogy is just brilliant, isn't it? Think about it. Each thread has its gun drawn, demanding a resource, but it's also being held at gunpoint for the resource it's holding. Nobody can move, nobody can back down.
And this breaks it down perfectly. So thread A has the key to vault 1, but to finish its job, it needs the key to vault 2. Meanwhile, thread B has the key to vault 2, but it needs the key to vault 1. Since neither thread will let go of the key it's holding until its job is done, well, you see the problem. They're trapped. Permanent gridlock.
So, if that's the problem, how do you fix it? How do you break the tie and get these threads to play nice? Well, the solution, as Margaret explains, is actually surprisingly simple, and it has nothing to do with using fewer locks. The solution is just one simple concept: lock ordering. This is the golden rule of multi-threaded programming. It's a simple decree that says whenever you need to acquire multiple locks, every single thread, no exceptions, has to get them in the exact same pre-decided order. This one rule sets up a clear hierarchy, a kind of path of entry that makes a standoff like this impossible.
And check it out, here's the fix in action. On the left, that's the deadlocked code. You can see that the transfer function from 2 to 1 locks vault 2 first. But on the right, look at the fix. Both transfer functions have been changed to always lock vault 1 first, then vault 2. Always. With that order established, if thread A has the lock for vault 1, thread B just has to wait its turn. It's not holding lock 2 hostage anymore. The standoff is just completely avoided.
And there it is. That's the light bulb moment for Timothy. This is the big takeaway, right? The locks were doing their job perfectly. The bug wasn't in the tool, it was in the procedure, the inconsistent order that he was using those tools. Margaret leaves Timothy with this really powerful piece of wisdom. She says, deadlocks are like ghosts. They're elusive. They might not show up when you're testing.
They might only pop up in production, once in a blue moon, when the timing of the threads lines up just perfectly wrong to create that standoff. And that's why your job isn't just to use locks. It's to design your whole system so that this kind of circular wait is structurally impossible from the get-go.
Okay, so how do we boil all this down into a practical guide? Well, to make the lesson really stick, Margaret gives him a cheat sheet, a quick reference for spotting and, more importantly, preventing deadlocks in your own code.
All right, let's run through Margaret's cheat sheet. First, remember the name of the villain, the deadlock. That's when your threads are just blocked forever. The cause is the circular wait. Thread A is waiting for B, and B is waiting for A. Now, your number one defense, your silver bullet, is the golden rule. Always, always, always acquire your locks in the same predefined order. But what if you can't guarantee the order? You've got a backup plan, the timeout strategy. This just means that when a thread tries to get a lock, it doesn't wait forever. It gives up after, say, 5 seconds, releases any locks it's holding, and then maybe it can try again later. It's a way to break the standoff. And finally, detection. If your program just freezes out of nowhere with no error, you should immediately suspect a deadlock. If you peek under the hood, you'll almost always find a thread that's just stuck, waiting to acquire a lock. That's your ghost in the machine.
And that brings us to the final and I think most important question, the one for you to think about. These deadlocks, these ghosts, where might they be hiding in your code, just waiting for that 1 in a million chance to bring your entire program to a grinding halt?